Okay, so welcome back to DSP. My TA, one of the TAs just asked me whether we should still keep the other room open, and my answer is yes, just in case you still keep my promise. I want to keep my promise. If you need to eat your lunch, you can go to the other room. Yeah, we have the privilege of having 2 rooms available. So no matter how late people come in and how many people show up, I think we want to keep our promise. Okay, yeah, so yeah. But thank you all for being here on time and in this room, because that encourages me a lot. So thank you very much. And okay, so we are on the topic. Today. We will continue the topic of filter design, right? Filter design. So previously we talked about IIR. Today we will be on FIR, finite impulse response versus infinite impulse response. Okay, so particularly we are going to use windows. So last week, let's do a bit of a recap. From last week, we said that ideally, taking a low-pass filter, for example, ideally we want the frequency response to be all 1 in the pass band and 0 in the stop band with a cutoff frequency, let's say omega c. Okay, yeah, that's ideal. And we know that by going back to the time domain, the ideal filter has an impulse response of the sinc function, right? Sinc function is its impulse response. Yeah. But sinc function in the meantime extend to both positive and negative side infinitely. 无限的延伸. Okay, so I would say that this filter cannot be implemented in the time domain. So in order to still keep it useful, we suggest that how about a strategy? Okay, how about we keep the middle part, right? How about we count from time minus big N to plus big N, right? Just keep the middle part and just truncate everything else. Just remove anything that's outside this window. Okay, window is something that we pay attention to, or we use. So this is let's say if the ideal response is H ideal, yeah, let's say ideal response is H, then our design would be simply to keep the middle part. Good. So by keeping the middle part, you can think of a rectangular window. You can think of a rectangular window, so we define Wn to be 1 between plus and minus n, and 0 elsewhere, outside. 0 elsewhere. So we define such a window, and so it should become pretty straightforward. So to just keep the middle part, we suggest just that our design is a result of multiplying the ideal response with the window, multiplying in the time domain. Okay, is that clear? So it's a very simple idea. Keeping the middle part means to use a rectangular window and multiply it with our ideal response. Okay? Very easy idea. Very easy idea. And we know that by doing this, when we multiply in one domain, we have what in the other domain, right? Convolution theorem, right? So multiplying in the time domain means the frequency, the spectrum is going to convolve in the frequency domain, right? So we know that by going to back to the frequency domain, let me be sloppy, okay? Let me just emphasize that the spectrum is a function of omega, okay? So this is a sloppy notation, because usually when we have been using this notation, right? But just allow me to be sloppy. Sloppy 知道意思吗？ Sloppy 比较随便一点啊，比较轻松，比较随便。Sloppy, yeah. Sloppy notation. SLOPPY notation. So let's say the frequency response is going to be the convolution of two things. One is the Fourier transform of the rectangular window to have convolved with the ideal response. The ideal response, okay, convolution. So there is a theta minus, omega minus theta, something like that. And now theta becomes a dummy variable that we integrate with. And the range should be from pi to pi, okay? Right. So with that, in the end of the lecture, I was trying to just show that the resulting response is not ideal anymore. Okay, it's not going to be ideal anymore, but still, it has a low frequency response. It tends to have ripple for the pass band as well as for the stop band. So there is you can see the edge of pass band and stop band and so on. Yeah. So resulting response will be frequency response will be this. Okay? Yeah. So that's a quick recap from last week. Yeah. So in this week, today, we are going to use other kinds of window, okay? Different kinds of windows. So today, so that's recap, okay? Yeah. Today, we'll have various types of window, okay? Not rectangular anymore. We can be more general than that. That's fine. So we'll talk about a few different types, and they have different names. Hamming window, Hahn window, Blackman window, Kaiser family of windows, okay? So all these are different ways to keep the middle part while modify a non-constant window. Constant window is a rectangular window, right? But we can argue that we will do better than that. Okay, we'll do better than that. But in order to define what is better, what is not so good, we need to consider two design factors. So last time we also mentioned that whenever we design a filter, we care about a tolerance, right? So how small can we keep the ripple to not exceed the limit, right? That's our tolerance, okay? So maybe your spec is you desire the tolerance to be so that the ripple will be between 1 minus delta and 1 plus omega delta, right? A small delta, yeah. Let's put a closed interval, yeah. You want the gain to be in between 1 minus delta and 1 plus delta with a small value, okay? So that delta is a tolerance, yeah. We don't want delta to be too big, right? As well as you can also in certain cases you may also distinguish between the pass band ripple and the stop band ripple. Okay, there might be another delta, but here in this semester I'm not going to cover the situation of having different deltas. Turns out that our spec is the same. Tolerance is the same for pass band and for stop band. Okay, so that's one design factor we need to consider. And the other design factor is what? Is how rapidly can we make a transition from pass band to stop band? There is always a transition width. Okay? There's always a transition width. Yeah, between the edge of pass band and the edge of stop band. So there is a transition width. I need to draw better. It might be too small when you're looking far from the back of the room, but there is a transition width. There is a transition width we may denote as something like delta omega. Okay? So ideally, we want to have narrow transition, fast transition between pass band and stop band. We want that transition to be pretty narrow. Also, at the same time, we want to keep the tolerance. We want to keep the ripple small. Turns out that these factors we'll show today, these two factors all trade off with two things. Okay? So kind of highlight. The transition width naturally is inversely proportional to the length of the window. Okay, roughly speaking, it's inversely proportional to the length of the window. Maybe 1 divided by 2n, add 1 if you will. Yeah, it's inversely proportional to the window length. Okay, let me just say 2n. Okay, because plus 1 is not that important. Okay, yeah. But delta has a different story. Okay, this ripple, the magnitude of maximum deviation. Okay, that ripple, the size of the ripple, it turns out that it is not as simple as having an inverse proportional relation. Okay, yeah. The fact is that you may keep using the rectangular window by increasing the window length. That's fine, and you will narrow the transition width for sure. But turns out that the ripple, the height of that ripple, will not be reduced. Will not. Okay. You want to reduce it, you want to suppress it, but it will not be reduced merely by increasing the length of the window. Okay. We'll come to that. So that's the kind of motivation behind the reason why we might need to consider using some other kinds of windows. Okay, so in general, there are two design trade-off factor between transition width and the height of the ripple. Okay, there's a trade-off, and we'll focus on this topic at least for the major part of today's lecture. So if time allows, then we will enter the next lecture, which is about high-pass filter and band-pass filter, and there's this thing called all-pass filter. Okay, a filter that lets all the frequency pass equally with equal magnitude response. Okay, so we will cover that. These are the topics for this week. And so I understand that yesterday was the deadline for some of you to turn in a 实作专题, the independent topic report. Yeah. So that's why I decided maybe we can take it easier this week. We will postpone the deadline for homework number 4, right? Homework number 4. The deadline has been postponed to Friday. Am I correct? Friday, right? Yeah. 星期五, Friday deadline. But with that, I also decided that maybe Thursday is, let's just keep, I'll be giving lecture. So today, no, this week, we won't have a follow-up discussion session as usual. Okay, but next week we will resume it. Next week we will have homework number 5, and we have a discussion session directly for homework number 5. Okay, yeah. So that's the plan for this week and next week. And the week after that, wait. When are we having midterm? Next week? Is it next week or the week after next week? The week after next week, right? Yeah. Okay. So midterm number 2 is 2 weeks away from now. Okay. 2 weeks later, when you come back, we have the midterm exam. And today, I mean this week is the second midterm will cover from where we left for the midterm to this week. Okay. So hopefully we will finish this lecture as well as the next lecture. That is all pass, high pass, and band pass. Okay. Yeah. Any question regarding schedule and administration, homework, deadline, and stuff? Yeah. Okay. So if not, let's move on. Right. So FR filter design using Windows. Yeah. And what do we have? So pretty much that's a kind of a diagram. We have tolerance of pass band and stop band. So, and these tolerance might be different, okay? But this semester we don't emphasize how to handle different tolerance. Okay? Yeah, if you're interested, there's something on the textbook would allow you to handle that. But this year, assume that we have equal tolerance for passband ripple as well as stopband ripple, and also there's a transition width counting from the edge of passband to the edge of stopband. Okay, so this is our transition width. So the idea of using window is really looking at the sync function, the ideal impulse response, and keep the symmetrically 对称. Remember, keep in mind that we keep symmetrically the middle part, maybe from -n to +n. Keep the 2n plus 1 points, 2n plus 1 samples. So now our our window has a finite length, and when we multiply the window with our desired function, this we can claim that this already is a design. Okay, this already is a design. Yeah, now we claim that this is design. Yeah, there is some thinking behind it. 有些道理在啊 there is some thinking. So this is our design, and the result, the multiplication in the time domain results in convolution in the frequency domain, and sometimes we call it cyclic convolution to emphasize that really the interval for integration is around the unit circle. Okay, yeah, cyclic 循环式的什么啊 cyclic convolution. And so that's that. But so we can easily plot. So there's a detail I might not have mentioned. Okay, there's a detail. So look at these plots. Either the plot I'm making on the board or the plot back in my next page, right? Back in this next page, this is a direct copy from the textbook, okay? Look at this response, right? This frequency response. So, and please pay attention that here, really, the gain can be, in this case, can be both positive or negative, and they are real numbers. Have you noticed that? Okay. Typically, when we talk about magnitude response, we take the absolute value, right? Typically, we do that. At least previously, when we talk about IR design, we put absolute values around our magnitude response. In this case, somehow, we don't need that. Everything's real after going to the frequency domain. Have you noticed that? Okay, have you noticed that? That's a question. Have you noticed that? Yeah. When you went home last week, 回家有看到吗？啊 And there's a reason. The reason is because our filter in the time domain after truncation, before or after truncation doesn't matter. But here, our filter has a nice property of symmetry. Even symmetry, there is an even symmetry in the time domain. Right after windowing, okay? Do you see that? Even symmetry means, so let me put a remark in here. Note that in here, H, the frequency response is real because what? Because H of minus n equals to H of n. And this is a property that we have discussed a long time ago. Long time ago, we talked about if we mentioned if we have even symmetry in the time domain, then that guarantees the spectrum, or in this case, frequency response to become real. Its Fourier transform will be real valued. Real, so sometimes it's positive, sometimes it might be negative, okay? Right. So this is really real, so there's nothing wrong here. And we can plot it this way without putting absolute value, and we know exactly what's going on because there is an even symmetry in the time domain, okay? But anyway, so last time I was trying to move this, what is this? This part. This part is the Fourier transform of the window, of the rectangular window. Okay? The Fourier transform of our window will have a main lobe together with a series of side lobes on each side. So we can imagine that when we move this theory. When we move the Fourier transform of the window left and right, and calculate the area is overlap with the ideal response. We are doing a convolution in the frequency domain, right? So I was trying to convince you that the resulting curve, indeed, you expect that it will be around 1, approximately 1 for the passband, and it will make a transition to stopband and having ripples out there. So I want you to be able to imagine what's going on here. When we calculate the area of the overlapping part, calculate this area while we move the purple thing left and right. Okay, as the purple thing is moving across to the to become not overlap with our ideal response, that's when the response begin to make its transition from passband to stop band. Okay, so please let us know if you have difficulty picturing what's going on. Okay, yeah, so that's kind of a way to illustrate frequency domain convolution between our Fourier transform of the window and the ideal response that we desire to design. Okay, we want to design. Okay, so a bit about the terminology. So here we have, for rectangular window, there's always a kind of middle part which we call the main lobe. When you take the Fourier transform, and in this case, indeed, we put parentheses. We put absolute value around the Fourier transform. Okay, so this is, we're talking about the absolute value of the Fourier transform big W of small w as a function of omega. Okay, so it has a main lobe in the middle, and the width of the main lobe denoted by delta omega m. Okay, the width of the main lobe is inversely proportional to the length of window. Okay, in this case, in this particular example on the textbook, the length of the window is 8. Yeah, is 8. I don't like that a lot. I don't like that at all because that again, there's I need to put another note right here. Okay, perhaps. So here, another note. This in the textbook, in this example from the textbook. In this example, the length of window is an even number. Okay? It's harder to imagine what's going on. Yeah. When we keep the middle part always symmetrically, it's never going to be an even number. Okay? So in my lecture here, when I say keeping the middle part, note that the length of window is an odd number. So there is a slight difference in here, okay, that could cause some trouble, okay? So technically, my way of design does not allow the window to be even number because I want to keep it the symmetry. Is that clear? Okay. But like overall, the idea is still true that when we increase the length of window from 2n plus 1 to 2n plus 3, you know, adding one sample on each side, and we can keep doing that by increasing the length of window on both sides. The idea is still true that the main lobe, the width of the main lobe is going to be inversely proportional to the length of window. And here we're talking about, this is an example of duality in Fourier transform, right? Wider in one domain, narrower in the other domain. Okay? Yeah, so this is an application of an example of duality. It's still true that when our m, let's say when m plus 1 is even, that will not occur in my lecture, in my suggestion. If you follow my suggestion, you will not encounter a case when the length of window is an even number. Okay, if you follow my suggestion, that will not happen. Okay, but if you just but the general principle is still true that I must have written it somewhere in here that when we increase the length of window, I want to show. When we increase the length of window, the main lobe width. When we increase the length of window, the width of main lobe decreases and the height of the main lobe increases. It becomes narrower and taller. When we increase the rectangular window, its Fourier transform is going to look narrower but also taller. Yeah. And how would that affect the result of our design? So I was jumping a few slides ahead to show you that this is what I was trying to tell you one more time, that the result of design, when we increase the length of the window, we'll have a narrower transition. We'll have a narrower transition because the width of main lobe decreases. Okay, we will have a narrower transition. So I was writing here. When we increase the length of window, the main lobe width decreases, and at the same time, the transition width also decreases. Consequently, consequently, 其实是两者是相通的。Consequently, so that's good. We desire to have a narrower transition, and you can always achieve that spec. You can always meet that spec of transition width by simply increasing the length of window. It can always be achieved by simply doing that, if you are able to afford it. Okay, that means computation time, computing power, energy, or as I say, any there's a trade-off. Better performance, higher computation cost. That's one example. But in the end of last week's meeting, I briefly mentioned that. However, unfortunately, this tolerance, the ripple, the height of that ripple will not be reduced when we increase the length of the window. There is also this largest ripple. This largest ripple and its height remains the same. However, we increase the length of the window. Okay. However many points you want to keep extending in the time domain to keep the larger portion of the middle part, you can do that. That will help you in transition width, but it will not help you in reducing the size of the largest ripple. Okay, should I write it down? Okay, so however, so let's put some mathematical notation a bit. So when we consider maximum of our result of our design, minus our desired response, okay? If we do that and search among all omega, the maximum deviation is the height of the largest ripple, right? Can we agree on that? This notation, the height of the largest ripple, the largest ripple's height, okay? The largest ripple's height can be expressed by this. We look for around all omega and see where it has the largest deviation from the desired response. Okay, here D, the letter D stands for desired. 我们想要的 desired response, which is ideal low pass. Okay, the largest deviation from ideal low pass, and put the absolute value here. That quantity is the largest ripple, the height of the largest ripple, and that it will not be reduced merely by increasing m. It doesn't help. Increasing m does not help us reduce the largest ripple, okay, largest deviation. And this has a name. This is referred to as Gibbs phenomenon. For those of you that are interested. Okay, Gibbs phenomenon. So roughly speaking, let me also make some extra discussion, okay, for Gibbs phenomena right here, kind of supplement. I have some remarks, for Gibbs phenomenon. Okay, So suppose that the length of Wn is, let's say, 2m plus 1, okay? And the resulting design is h of n, is impulse response is h of n. So, but let me add a superscript n to emphasize now this design is keeping the middle 2n plus 1 points, okay, equals to w of n times the ideal response, okay, yeah. Maybe I should also put a parenthesis around here, okay, yeah. So we have limit, this is quite tricky, it's really interesting. N approach infinity h n equals to h dn. Of course, right? Can we agree on that? When we keep more and more of the middle part, in the end, the two functions become equal. Okay? Yeah. Is that right? Yeah, we keep more and more of the middle part, right? In the end, in the limit, when n approaches infinity, the two functions are the same functions, right? Yeah. So doing a Fourier transform, we can say that, yes, therefore, a limit h of the resulting frequency response should also approach the ideal response, which is this ideal response. Ideal response is having constant gain in passband with the cutoff frequency, and it just all of a sudden goes to 0 for the stop band, right? This is ideal response. So can we say that this is true? For all omega, okay? For any omega. Let me say for any omega, okay? The equality holds in the limit for any omega, okay? For any omega, right? But the funny thing is that limit n approach infinity, the maximum deviation between our design and the desired design, this thing does not approach 0. Yeah. Or should I emphasize that it approaches a small value, small but positive value, okay? This is kind of the mathematical way to formulate, to state, to describe Gibbs phenomenon. Even though the function limit is the same, but the error, the maximum error, does not approach 0. Okay, this is Gibbs phenomenon. So here, yeah, please take a look. Please take a look. There's no contradiction. This is, everything is correct here. Yeah. If you, for any simple error, please point out. Okay, yeah. But I want to deliver the kind of a clear message. In this case, we encounter a situation when the function limit is in the limit the function equal. The two functions equal when you take the limit when n approaches infinity, pointwise. Okay, for every omega. That is to say, for any omega, this equality holds. The limit is approaches our desired response, okay, for any given omega. But somehow, if you look across all omega and talk about the maximum error, maximum approximation error, that will not converge to 0. Yeah, it doesn't converge to 0. However large you increase the length of window, okay? There's always a finite non-zero error there, okay? And it has something to do with the meaning of convergence. What do we mean for a function to converge, for a sequence of functions to converge to a function? Let me say that again, okay? Maybe in Chinese, okay? 这个跟什么有关呢？ Let me explain in Chinese, okay? 这跟什么有关？跟这个如果有一序列的这个函数，它们会趋近某个函数这件事情啊。When we talk about a sequence, 序列啊，a sequence of functions, and they approach a function pointwise. in omega. In this case, omega or f of x. Yeah. When we talk about the convergence of a sequence of function to a target function, we need to be careful. Okay, there's a theorem. It turns out that there's a theorem in advanced calculus that talks about uniform convergence. Yeah. The key word is uniform convergence. The key word is uniform convergence. So roughly speaking, there's a theorem that tells us if there's a kind of convergence called uniform convergence. Okay, and when a sequence of continuous function converges to a sequence uniformly, the limit function will also be continuous. If f n x converges to f of x uniformly, and each f n x is continuous, then f of x must also be continuous. So this is just to show you that this is 蛮深的啦, that there's a depth in the theory behind this, or Gibbs phenomenon. Okay, so the situation we have here is that we have a sequence of functions, a sequence of functions that converges to a function. Okay, but this function is not continuous, right? So how do we apply this theorem? Even if you don't know the meaning of uniform convergence, we can still practice, okay? We have a sequence of functions that converges, when n approaches infinity, it converges to a function, okay? But this function we know is not continuous. It has a discontinuity at the Claude frequency, right? So therefore, what can we conclude? Even without knowing the meaning of uniform convergence, therefore, we can conclude that the convergence is not uniform. Okay, the convergence is not uniform, and that turns out to be equivalent, saying that therefore, Gibbs phenomena must happen. Okay, that the error the maximum error never goes to zero. All right. So I think I need to stop here. This is just to show you that if you want to have some extended reading, self-study, right? Study this at home. This is a topic about uniform convergence of a sequence of functions. Okay, sequence of functions. So the message is that there's always a non-zero ripple, and you cannot simply reduce it by increasing the length of your rectangular window. So what should we do? So the best we can do, if this bothers you, okay, but if it doesn't bother you, fine. 躺平, we don't care. Then if it doesn't bother you, that's end of story. But if this bothers you, 你们有 concern 吗？看彼此啊。If this bothers you, then we need to talk. Okay, we need to find a way to suppress this. If you are unhappy about this ripple, you want to really reduce it across the entire passband, okay? Then we need to have a better strategy and improve our strategy by allowing to use something other than the rectangular window, okay? So that's our next topic. Our next topic is a few different kinds of windows, right? A few different kinds of windows right here. So here is also just a plot from the textbook, okay? Any questions so far? Gibbs phenomenon. Okay, the maximum ripple has something to do with uniform convergence. The idea of something converges uniformly. But here to reduce that the size of that ripple, we can try instead of a rectangular window that goes from 0 to m. Okay, But here I want to emphasize that by now. yeah, before we talk about different kind of window, let's make sure that we understand this. So last week I mentioned that there are two steps of designing an FIR window using rectangle window. First step is to keep the middle part. But then right after doing that, you found that strictly speaking, 严格来讲啊, strictly speaking, this filter is non-causal, right? By definition, it is non-causal because the impulse response has non-zero values in negative time, before time zero. Okay, so this is non-causal. So simply to use it when you want to convolve this impulse response with your signal to perform low-pass filtering, we need to shift. Just strictly speaking, we need to shift the shifting the entire thing to the right by n point to make it causal. This is very simple, okay? To perform a shift by n point. So now our filter lasts from time 0. The first sample is time 0, then the last sample becomes time 22, okay? Time to n, okay? So now the time lasts from 0 to 2n, okay? So that's what's going on here. So now we suggest that instead of using a rectangular window which has a length of n+1, how about we shape the window in the time domain? How about we have a non-constant shape, let's say bell shape, in this case. How about we have a bell-shaped window? And seriously, this is our new W of n, okay? And in this case, let's see. This case, we have the window is called Hamming window, and we'll see the expression, okay? There is a Hamming window, and similarly, there's the Han window, dash line, 虚线. The dash line goes, let's take a look. It goes from here, and now it touches 0 at both at the edges. We have the Han window, which touches 0 at both edges, and so on. We can also connect a straight line. Let's say make a triangle. I'm sorry. Let's say this is a straight line. Right. This is a straight line right there. Connect them and call this is simply a piecewise linear function, if you will. Piecewise linear function, and it also has a name. Sometimes people call it Bartlett. Okay, the names are not that important, but that's also kind of something that we may want to try. Okay. Using this window, or finally, there's a classic window called Blackman. Blackman also goes to touches 0 at the edge, but it sort of become more smooth. It is more smooth. The degree of smoothness, 它那个 smooth 的程度the degree of smoothness is the greatest between. Here we have 3 types of window that all touches 0. At the edge, but the Blackman window touches 0 most smoothly. 最平滑了, most smoothly. It touches 0 most smoothly to compare with, right? Whereas the triangular window, it touches 0 sort of, but then there's a sudden change of slope, right? But for Han window, it touches 0 and there's no sudden change of slope, and that is good. It's smooth. To the second order. And Blackman window further improved from that. It has the smoothest among the 3 windows that touch 0 at the boundary of the window. Okay, all the same length from 0 to n, having n+1 samples. Okay, So far so good? Okay, So different kind of windows. So now we have the time domain shape, and here I want to show you a few equations. I don't need to show the equation for the triangular window, right? 三角形 triangular window. There's no need to show the expression. Just connect a straight line, okay? Nothing more, nothing less. But for the Han, Hamming, and Blackman window, let's take a quick look. The Han window has this expression, okay? In the time domain, it equals to 1/2 minus 1/2 cosine of that. And now I believe our time is from 0 to m. That's the duration of the window. Okay, the duration of the window is from 0 to big M. Okay, yeah. Oh. Here also duration is from 0 to big N. So the Hamming window, the Hahn window, differs only in the coefficients. So here we allow the Hamming window to not touch 0, right? 0.5 minus 0.5 becomes 0, right? But 0.54 minus 0.46, 0.54减掉 0.46, right? Doesn't equal 0. So it's a very simple difference between Hahn and Hamming. Very simple. They look similar. One touches 0, the other doesn't. Okay? And then finally, the Blackman window has 3 terms in the time domain. In the time domain, we have 3 terms. Okay? So we add one more term of cosine. By adding one more term of cosine, we can adjust the coefficients to make it maximally smooth. Okay, yeah. But anyway, so anyway, they are there. Okay, they are there. So sometimes these windows are called they are said to belong to the cosine family. Okay, we have the cosine family of windows because the explicit expression has cosine. Okay, so they are called the cosine family. We have family of 3 windows already. Okay, 3 of them in the time domain. So we can now look at what? We can now look at their Fourier transform. Okay, we can now look at the Fourier transform. So when we go to the frequency domain and plot, let me enlarge this. The usual way we plot the Fourier transform. When we plot the Fourier transform, you can consider using dB scale. Taking the 22 log 10, okay? Take 20 log 10 and we have dB scale. So we will come back to take a closer look, but I want you to now maybe spend some time to pay attention to the difference. What do you notice? What do you notice in terms of main lobe and side lobe, okay, when they are plotted in dB scale? So when we come back in 10 minutes, we will have a discussion together. In dB scale, what do you notice, right? Yeah. So let's have a 10 minutes break. 好，安静下来。What time do we have? Okay, still 1 minute. Yeah, until the end of the break. Okay, I think the bell is ringing. Okay, yeah. Bell is ringing. All right, so here we have 3 windows. Okay, please take a look. Let's look at the plots together. What did you notice? Tell me 10 places they look different. 请找出10个不一样的地方啊。Of course, yeah, they look different. Yeah. Most obviously, right? Anybody? 保证没加分. Any difference? Yeah. Yeah, decay, right? That's good. Decay. What else? Yeah. I want 3 differences. Yeah. Decay is different. Yeah. What else? Or in Chinese? Yeah. Yeah. What else? 什么东西？第二个怎样？没有碰到。Oh, okay, yeah. So it's pretty flat, right? 看起来比较很平. Okay. So the second plot looks flat. All the side lobes, right? What else? One more. Yeah. Main lobe, the size of main lobe, great. That's good. Okay. So I would say that there's yet another difference. So let's summarize. Okay. So first, let's note that for the Han window, it's pretty special. All the side lobes right here, they appear to be pretty flat when we extend the frequency. All the side lobes are pretty flat. And secondly, for the other 2 windows, there is a decay of side lobe. When the side lobe goes farther and farther away from the main lobe, their height decreases. Okay, so that's a difference. Yeah, and also thank you for pointing out that the main lobe width. Note that all 3 of them have the equal length in time domain. The length in time domain is m+1. Okay, all 3 of them, or roughly m. But here the main lobe is widest for Hamming. Okay, yeah. So let's kind of write it down. Main lobe width. The main lobe width is largest for the Blackman window, for the 3rd one. Okay, its main lobe width is the largest among all 3 of them. Is it good or is it bad? It's bad, right? That's bad. So this is bad. But what's cool about this window is that its its side lobe has the most suppression, most contrast compared to the main lobe. And this is important. This is good. Okay, there's a side lobe. There's distance between the height of a side lobe to the main lobe, which is normalized to 0 dB. Okay, this difference here, right here, is the largest. This margin is the largest among all 3, right? In here is more than approximately 60 dB. The side lobe suppression ratio. The side lobe suppression ratio, we call it, is 60 dB, 60 dB, which is the largest among the 3 windows. And that's good. This is a good thing. Okay? So this is bad. This is good. Okay? Please make a meme. 做一个 internet meme. Good or bad? Yeah. But how about now comparing these 2 things? Now, if as much as the side lobe ratio, suppression ratio is concerned, Hamming is better than Han. Okay, Hamming is better than Han. For the Han window, the side lobe suppression ratio here is around, let's say, around 30 dB. And here is more than 40 dB. Here, this margin is 60 dB, right? So you can also compare the first side lobe, high side lobe, in terms of that, Hamming is better than Han. But then there's also some sort of a trade-off. Yeah, that's in that here, all the side lobes are, the side lobe remains similarly large, okay? When you go away, there's no decay, and then that might not be bad, okay? No decay here, no roll-off, okay? That's the way we call it, no roll-off. There's no roll-off of the side lobe. And that might not be desired, okay? It might not be the best thing to have, best property to have, okay? So already that by comparing 3 windows, you see there's an issue of main lobe width. We want it to be narrow. And there's also an issue of the side lobe suppression ratio. We want that to be high. And these 2 factors are important because, as we'll see in the summary, there's a chart, there's a table we'll look at. Because main lobe width is directly, I would say, directly proportional to the transition width of your result. Remember that we use the window to convolve with the ideal response, right? And that gives us an approximate response with ripples, right? So it turns out that the ripple is directly related to the side lobe suppression, this factor, okay? When we have better side lobe suppression after calculating the Fourier transform with the window, this leads to better performance in terms of reducing the ripple right here. Okay, they are closely related, because that's we are moving the window transform in and out of across the edge, right? When convolution, when you perform convolution, you'll see that the side lobe, the height of the side lobe directly relates to the size of the ripple for your filter. So the filter you're going to get, okay? So we want this to be large, but at the same time, we also want this to be narrow, okay? So in Hamming window, so if you really care about the ripple, you should apply, we suggest you might want to try Blackman. And the take-home message, another message is that if you care most about transition width, then Hamming and Han might be your choice rather than using the Blackman window. Right? Because here we sacrifice by having to have a larger, wider transition because the main lobe itself is wide. Yeah. So it's a very simple idea. So you get used to it. Okay, 2 factors: ripple and the transition width, and the 2 of them directly relate to 2 factors in your Fourier transform of the window. That is, ripple is related to the side lobe suppression ratio, while the transition width, of course, is related to the width of the main lobe. Okay, yeah. So these are keeping when you go home, just make sure that you keep these factors in your mind, how they decrease, how they increase. Yeah. So you'll be fine. So otherwise, we have another slide showing the Fourier transform of rectangular window and Bartlett window, and you can also compare them. Okay, yeah. There is also the suppression ratio right here, as well as the roll-off. There may be some kind of roll-off, as well as the transition width. Okay, so the next page summarizes all the performance indexes of all these windows. Okay, let's take a look. So here is the peak side lobe amplitude relative to the main lobe. Okay, relative to what? Relative to the main lobe. Relative side lobe amplitude. Okay, here we see that rectangular window is -13. Okay, and then we have it keeps getting better. Okay, keeps getting better in this order. We want it to be this relative amplitude to be as low as possible. Okay, so here we see Blackman is nearly -60, 几乎是-60 So this is the best. But approximate main lobe width. Now we know that this directly relates to transition width of your design. Transition width of your design. Okay. So if we keep the same M, the same length of window, so here note that M is the same, but the width of main lobe is roughly 4 pi divided by M, 4 pi divided by M, but 8 pi divided by double the width, okay? The width is doubled whenever we use Barlett-Hahn or Hamming, doubled and tripled for Blackman, okay? Triple for Blackman. So that's the second column, okay? Main lobe width increases as we go down the table. Okay? As we go down the table, the main lobe width increases. And what else? The third column, let's look at the third column. This is the ripple we're talking about. Peak approximation error, the Gibbs phenomenon that we cannot simply reduce by increasing the length of the filter, okay? So now we are comparing across different types of a window instead. Okay? When you attempt to make this better, you need to consider choosing a different kind of window. Okay? So as a consequence of this order, we know that from rectangular all the way to Blackman, the performance here seems to improve one after the previous one. Okay? This performance increases in this order, then therefore this performance also increases in that order. Okay? So it gets better and better from -21 to -20. So we want delta to be small, so we want this to be more negative, right? Delta is here. Delta is right here. 1 plus delta, 1 minus delta. Okay? So the largest deviation that's called peak approximation error. Okay? The largest deviation of your performance from the ideal, across all frequencies. The peak approximation error, taking dB scale, it keeps improving when we go from rectangular further down, finally to Blackman. But the trade-off is there. Transition width is the widest while we achieve the best approximation error. Okay? So the frequency response will be most ideal for Blackman, but the transition width is wider. Okay? All right, so any questions so far? So far so good? Take a look at the window. It tells us a lot of, this is seriously, this is a table that you can refer to when it's your time to design a window, design FR window. Okay, please refer to this window. But not window, please refer to this table, okay, window table, right? So, if there's no questions, you must have noticed that there are 2 additional columns right here, okay? So next we will be covering Kaiser window with the parameter beta, okay? With the parameter beta, we'll talk about that. It turns out that we can tune, the idea for that is to tune a window continuously with a continuous parameter. We'll go to that. But before I move on to Kaiser family of windows, let me point out one remark right here. So let's come back to this slide. One of you approached me during the break, during a 10-minute break, to ask about, to confirm about the time axis. Here, time goes from 0 to m, right? Here, time goes from 0 to m. So I want to clarify. So to use this slide, the design procedure should be clarified, okay? So the design procedure should be first, decide on how long you want the window to be. Okay, let's say m is an even number. Right? To simplify our discussion, let's say m is an even number. Decide on m. Yeah. Do you know how many points you want to keep the ideal response in the time domain? Okay, decide on m, which is an even number, such like 22. And then second step, you want to shift your ideal response to the right by m by 2 m divided by m over 2 samples. Is that clear? By m over 2 samples. We want to shift it to the right. So now the edge becomes 0 times 0. Is that clear? Shift this to the right. Decide on your m first and then shift it to the right by the m over 2. So that now your window can start at time 0. Okay? Now after that, we say your design. Oh, now I'm sorry. I should put a D around here. Okay, D meaning desired, and then your design will simply again be the same. W of n times this h tilde after shifting. That's how we use this chart, this plot. Okay, so that your window is aligned. The window starts at time 0, while the middle of the window is aligned with the middle of your ideal response. Is that clear? Should I repeat that? Make the necessary shift so that the middle of your window is aligned with the middle of the ideal response. 中间要对齐至中对齐 okay, align them. So make the necessary shift so they align in the middle. 中间对齐 align in the middle. And I have another remark, okay? I have another remark. Before and after shifting, okay, there's a remark regarding the shift. We know that when we say h tilde is shifted, is a result of shifting our ideal response to the right by m divided by 2 points. Okay? We know there is a shift theorem in Fourier transform, right? We've encountered that many times by now. So we know that you all know that now the desired response with tilde is equal to what? The ideal response with a e to the minus j omega big M divided by 2. There is a phase factor, linear phase factor. And this is an application of shift theorem. And we know that this is real. And we also know that HD omega is real. Also, we know that, right? Because of symmetry. Ideal response. Wait, let me see. No, I mean, this response, both of them, Wait, what am I trying to say? What am I trying to say? Not ideal. So there's a kind of subtle thing, whether we shift first then align, or we multiply first then shift. Same thing. The result is going to be the same. Okay? So I'm getting a bit sloppy in my notation, but let me try to see what's going on here. So, let me draw a picture. Okay. I was trying to say so let me stick with my original plan. Our original strategy is first ideal response, which lasts forever on both sides. This is ideal. And then this is ideal. And then we shift it to the right by n points to begin from time 0 to time m, with now the middle is at m divided by 2. So that's the result of shifting. Okay? That's the result of shifting. And that's what we call HD of n. Okay? So let me erase this first. Okay, yeah, we know it's real, but yeah, we know the shift. What shift will shift anyway? Shift corresponds to a linear phase term. But I want to say that now, to summarize our picture, we would apply a window, right? We've been saying that we will apply a window. And the window might be, let's say, a triangular window. Okay, let's take triangular window as an example. So let's say we apply a triangular window, which is symmetric in time. Okay, let's say we apply triangular window from minus m. Yeah, I need to move it up. Yeah. Let's say we apply a triangular window W of n. And our design becomes H of n before shifting. Okay, now everything, let's go back to, we'll talk about shifting later, right? H of n becomes W of n times the ideal response, okay, from here, right? And we know that since W, know that in all the windows we talked about so far, and I've never encountered an exception, okay? In all the windows I ever applied in my life, the window is always an even function. All right, in all the windows I've ever applied, 25 years of career, I've never encountered a non-symmetric window. Okay, so all the windows have this property. Since it has the even symmetry, as well as the ideal response is also even symmetric. Both of them are symmetric. Turns out that we have the result of our design is also going to be even symmetric, evenly symmetric. Whichever type of window you choose, okay? I've told you that at least in all my life, all the windows I've used for filter design are always even, okay? Are always even function. So therefore, we have this property. This is your design, okay? This is your art, your design, something you should be proud of, yeah? Your design, your product that you handle to your client, okay? Yeah, so therefore, we know by Fourier transform H of omega, the result of your design is real valued. Yeah, this is what I want to emphasize, okay? And yeah, of course, later I mentioned that there's an issue of this filter being, strictly speaking, being non-causal. Then we shifted, right? Yeah. But now, here I want to say, yeah, sure. Then there's the issue of your final design. Let's say H final. Your final design of n should be shifting this to the m to the right by 2 over m over 2 samples. Okay, that's your final design. So therefore, your final frequency response should be related to your original frequency response by a linear phase factor. Yeah, maybe that nicely summarizes in the message I want to deliver. Okay, yeah. Let's take a pause right here. Let's stop right here and take a look together. Okay. Let's spend some time on this. Let's spend some time on this. Okay, yeah. So therefore, we have some names to introduce, right? In some textbook, this filter is called the zero phase filter. This is called the zero phase. This property that the frequency, the Fourier transform is real, sometimes it's called the zero phase. This is a zero phase filter. Whereas after shifting, since now there's this extra term right here, so this thing is called, the result here is called a linear phase filter. And these are just names. These are just names. Not difficult, okay? Just memorize. Zero phase filter, linear phase filter, okay? But what's important is their group delay. If I ask you, what's the group delay of both of them? What's the group delay? So the nice, important message right here is, what is the group delay? That's an important question to ask. So if you think about this, when the filter is real valued, the phase is basically zero, right? Or if when it's a negative, then the phase is pi, 0 pi. So the slope, what is the slope? For h of omega, the partial derivative of its phase with respect to frequency is, 0 everywhere. So the group delay is 0 across all frequencies. And I share with you, this is a nice property. Having a filter and the group delay is, there's no group delay, okay? There's no group delay. This is a nice property. That means if we have different frequency components in your input, and they arrive at the same time as the input, then when they come out of the filter as an output, they also occur there at the same time. The delay is the same across all different components. And that's a very nice property. That's a very, very nice property. Okay? That's a very, very nice property. Yeah. Wow. Good job. All right. Good job. Very nice property. All the frequencies suffer no delay. But unfortunately, we know it's impossible. This filter is non-causal, right? So therefore, after shift, the next best thing is that after the shift, that for our final design after shifting, and you can easily verify now the tau group delay defined as minus of partial angle of h final. Yeah, I forgot final right here. H final of omega, partial omega, right? That's the definition of group delay. What is it? Now, if the original has zero group delay, in theory, now with this linear term, you know that the group delay is going to be a constant of m divided by 2. Yeah. Constant. Good job. Okay, good job. Good job. Okay. This filter is causal. Its length is m, and it just gives the same delay to all the input components. Okay, your input signal may consider different frequency components, different wavelets. Maybe a broadband signal be consisting of many different components across a frequency range. But when at the output, the filter may give them different gain, pass band, stop band, right? Some will be rejected, some will be passed. But when they pass, after in the output side, the filter, all the components going to experience the same delay. So there's nothing as first in, last out. There's no such thing. Okay, all the frequency components will occur with the same delay. Okay, and that's a very nice property. And I share with you for audio. Let's say for music processing. Let's say you design a low-pass filter to reject certain frequency across a high C, right? Yeah, low-pass filter. And so this application in music, which is my field, let's suppose that like you process drum, like percussion, this kind of sound, okay? So percussion is short, that's drum, percussion, drum beats. Yeah. So you process the drum beats with a low-pass filter, using your design HD and multiply by your choice of window. Yeah. So this is X, this is Y. Yeah. The shape of the output is going to, of course, going to be different from the input, but all the frequencies are going to experience the same delay. So that means that short impulses remain short. Okay. In the time domain, the beats will not be spread. Okay. So in the output, the linear phase filter guarantees that, of course, there might be a delay. There might be a delay of, let's say, a delay of m divided by 2. But then, when the jump bit occurs m divided by 2 samples later, they are still kind of pretty much concentrated in the time domain. There will be no spreading. All the frequencies are still synchronized. All the frequencies still synchronized, still in sync. Still synchronized, 保持同步. They are still in synchronization. And that's a very nice property. Okay? So that the drum beat is not spread in the time domain. Does not suffer from spreading in the time domain. So in Chinese say 这个声音哈 ，in Chinese 就还能够保持着清脆啊，清脆声音能保持清脆。There's a like crispy clarity in the drum sound when you apply linear phase filter, because all the components are going to occur. If they occur at the same time in the input, they occur at the same time in the output, maybe with a delay of exactly 2m divided by 2. That's a very nice property. Okay. That's a very nice property that IIR filter does not have. Okay. In contrast, IIR filter such as what? Butterworth. Such as in your homework number 4. Does not exhibit this property. Exhibit this property of tau g equals to constant. It does not exhibit that, and there's a reason. Okay, that's your homework number 4. So it's good at this point, at this moment, to take a look and compare IIR and FIR. Okay, All right, Okay, so having said that, I want to proceed with Kaiser windows. Okay, any comment? Are things clear so far? 我们可以稍微停一下 Before I move on to just quickly talk about Kaiser family windows. Okay, so this is my field. Okay, my field is audio signal processing, 音讯, 声音 sound processing, sound engineering. That's my field. So I can share with you some insight in here. And maybe there's some other insight from telecommunication. Okay, for those of you that eventually will become and will be doing telecom research, there may be some other applications, some other scenarios why we prefer FIR rather than IR, or the opposite. Okay, or the opposite. All right. Now, okay, so let's come back and briefly talk about Kaiser family of windows. The Kaiser family of window, now let's go on to this page. In this page, I will just quickly write down the definition. Okay, so but let's take a look at the picture first. Kaiser family of window is parameterized by beta, by this variable called beta, denoted as beta. This parameterized, 有参数化啊. So we have in this first plot right here, we have three different betas. Beta equals to 0. Turns out that you'll see beta equals to 0, that's equivalent to rectangular window. When beta is 0, it's simply rectangular. But then we can also increase beta so that the shape looks more and more narrower and narrower in the time domain, more bell-shaped. Okay, when we increase beta. When we increase beta, the shape in the time domain of these windows in the time domain, they look more and more narrow until it looks like it almost touches 0, but never quite. Okay. So you can kind of have a feeling that when we increase beta, the shape looks more and more bell-shaped. And as a result, by increasing beta, the main lobe width becomes wider. The main lobe width becomes wider, but with the large beta, we can have the best, what? Best of what? We can have the best peak approximation error. So that's a kind of a continuous, 连续的 continuous way of trading off between two design factors, right? We know that we want the main lobe width to be narrow, as well we want that that side lobe suppression ratio to be high, right? High in side lobe suppression ratio, but narrow in the main lobe. And we know that there's a trade-off. But now, the Kaiser family of window with the parameter variable beta allows us to systematically trade off between these two desired goals. Increasing beta, then we just can achieve beta suppression while sacrificing in the main lobe width continually. So instead of having three windows, the cosine family has only three members, right? Cosine family has three members, but Kaiser family window is continuously parameterized by beta. So in principle, you can have infinite choices. Any beta is a real number. Beta does not have to be integer. So beta is a real number. Beta can be fractional. Beta 可以是有小数点. Beta is a real number. Typically in between 0 and 6. Let's say 0 less than beta, less than, you name it, something like 6 or 8. I don't know. Something like that. And of course, just further detail, you can make the comparison by fixing m. This comparison is there because we fix m. Okay? So here I want to just point out that in the first two plots we have a fixed m, but when we change m, that's the third plot. With the same beta equals to 6, but change m, then we, of course, you see that the side lobe suppression stays the same when we increase m, while the main lobe width decreases when we increase m. This is increase m. Right? So fairly easy to understand. But now, before we leave, I want to kind of, just for the sake of covering the topic, I want to show you the formula. What exactly is the beta function? Not beta. What exactly is a Kaiser window? Okay, in what expression? Is there any cosine, sine, or exponential or something? Right? You may care about that. Yeah. Well, any questions so far regarding how to read the plots? Okay, we have increasing beta. Beta is a variable we can tune, and we can trade off. Okay, but let me tell you that I'm just in the next few minutes, I'm just copying some equation from the textbook. So you don't need to write it down because you can find it in your textbook. Okay, I'm just going to copy that now. Kaiser family window, for the window itself, has an expression that involves Bessel function. Bessel function I naught with beta occurring right here. Really, you don't need to copy this. You can find it in your textbook. Okay, but 1 minus n divided by subtracted by alpha divided by alpha square, and evaluated and put it inside this Bessel function. This function is Bessel function. It's what we call zeroth order modified Bessel function of the first kind. Now, zeroth order is a kind of Bessel function. Modified Bessel function of the first kind. Wow, long name. Yeah. And there's also a normalization factor we need to consider. Okay, yeah. So that's an explicit expression for the window in the time domain. Okay. Now you see beta in the expression. And of course, this is where alpha is equal to half the window length, and we evaluate this is occur from 0 to m, and Wn is 0 elsewhere. Okay. Yeah, so that's an explicit expression. And for those of you that are interested in this zeroth order Bessel function of the first kind, zeroth order modified Bessel function of the first kind, let me just draw a kind of plot. Just imagine this is exponential function, but it's more suitable. It's similar to an exponential function. Okay, so it's like that, and it's evenly symmetric. I beta is like this function. Yeah. Okay, so that's kind of some extra information for you to know. But what's more useful is really this next slide. I do want to spend some time. We still have some time to talk about this slide. Okay, yeah. So now, this slide. Okay, yeah. Let's take a look together. For this slide, we are seeing the trade-off. Okay, it's a nice way to visualize first the trade-off between two factors: the transition width, however you design your filter, the transition width trades off with approximation error, the peak approximation error. So typical, and turns out that miraculously, I see this works miracle. I don't know exactly why, but all the Kaiser window, when we put their performance in terms of these two indices on the space, on the plane, we see that when we increase beta, they almost form a perfect straight line. And I don't know exactly why. Okay, yeah, this is, I say it works a miracle. Okay, it's like a miracle. But what's more important that somehow the people here are so smart that somehow your cosine family window underachieve. Yeah, the Kaiser family windows outperform the cosine family window, all three of them. Right? In the cosine family, here is the cosine family, right? Their performance is on the top right side of this linear regression straight line. That means, for example, for the same transition width, let's say here, for the same transition width, this is how we read this plot. For the same transition width, Kaiser can have a better approximation error, a smaller approximation error. Or you read this way: for the same for the same approximation error as Blackman, Kaiser has a narrower transition width. So Kaiser is the winner. Kaiser is better than Blackman. Kaiser is better slightly than Hamming. So Hamming is has some nice property in here on this plane. And Kaiser is better than Hanning. Now, let me just remove the last three letters. Okay, for some. Who is Amy Chen? Uh-oh. Amy Chen. I've known a few Amy Chens. 我认识一些陈 Amy, many of them. My aunt. Why? Jim, Amy Chen. For some historical reason, Hanning. Now we use Han. Okay, Hanning is a misnomer. Hamming is a person. Hamming. This is a person's name. But Han is also a person. That's the correct way to call this window. But in some contexts, sometimes in all contexts, we have Hanning and Hamming, which is a major source of confusion. So please erase the last three letters, Han or Hamming. Okay. But the point here is, Kaiser family of windows, when we parameterize them with a variable beta, and the expression involves a Bessel function of some kind, okay? Turns out that we can continually tune the side lobe suppression ratio as well as the main lobe width. We can continuously trade off between these two design parameters. And therefore, consequently, when we move on to the end result, end performance index, between transition width of the filter and the approximation error of the filter, we see that Kaiser window is a winner. Okay, Kaiser family window is a winner. So I guess that's probably all I want to cover for today. And tomorrow, when we come back, we continue into the next lecture. Okay. Again, thank you for being here. See you tomorrow.